In this video, I'd like to show you how to do some basic flow analysis. So I'm going to go here to the flow application on the ribbon. It's the fourth icon, and I'm going to select it. You can see we've got an image of the ascending aorta. It has not been segmented yet. This could have been done through pre-processing automatically, but in this case it wasn't done. So you can see aorta is selected here. I'm going to click on the lightning bolt, and it will automatically find the ascending aorta and segment it for me. Now, it is possible to edit these regions of interest. For instance, one can go ahead and click on the region of interest to activate it, and one can choose to copy and edit from current to end. One could copy the ROI from a previous phase or copy it from a later phase. One could shrink the ROI, or one could expand the ROI. And of course, one can always modify the ROI either by drawing it or by using a nudge tool to adjust it. Now I can also do that for the main pulmonary artery. I can choose a series that includes the main pulmonary artery. I can select the pulmonary artery category. I can choose a different color if I like, and then I can click on the lightning bolt, and again it will know to segment the main pulmonary artery. And it will apply automatically, if the preferences are set, a baseline correction which is based on the static tissues. Alternatively, one could choose to apply no correction or a static background ROI, or one could choose a series if there was a phantom to do phantom correction. I'm going to leave the auto correction, which is typically what I do in my practice. Now, if I want to compare the flow from the aorta and the main pulmonary artery, I can go ahead and click on the QPQS, and it will summarize the aortic and pulmonary artery values and calculate the QPQS for me. If I go back to the pulmonary artery and I want to see if there's any regurgitant flow, I can simply come down here and select regurgitant, and this white shaded area here is integrated, and it will report the regurgitant volume and the regurgitant fraction. If I want to see more detailed quantitative analysis, I can click on this report icon, which will give me the flow results in a summary table or the individual results on a phase-by-phase basis in this flow table. Now, what if there is aortic stenosis? How would we go ahead and deal with that? Well, this patient has aortic stenosis. I'm going to click on the series here, and I'm going to choose the cross-reference image to show you a stack. This represents a stack of images through the left ventricular outflow tract and the ascending aorta, which can be seen here. And I can step through the different images, and you can see the purple image is the active region of interest. So what we do is we choose the slice that corresponds to where the aortic valve is most narrowed. And we can come here to the flow category, and I can click on the lightning bolt, and it will automatically segment the aortic root. And if I go to flow, you can see several things. Number one, the flow has a yellow triangle with an exclamation point. This is an indicator that the baseline correction failed. So if we don't get a good fit to the static tissues, it alerts us that the flow correction may be suspicious. That doesn't really matter very much for assessing peak velocities. It is an issue for assessing bulk flow. If you want to shut off the baseline correction and see what the data look like uncorrected, you can see they're not very different in this particular case. Now, if I want to see what the peak velocity is and calculate a pressure gradient, I can come here and click on histogram mode. You can see this is a graph of the different pixel velocities within our region of interest as a function of cardiac cycle. It's a little bit difficult to tell what's going on here because we've got a lot of noise. And that noise exists because of intravoxel dephasing. When we look at the magnitude image, we can see there's some areas of signal dropout, and that gives us unreliable phase data. And so what we want to do is exclude noisy pixels. So I'll click here, and this will eliminate certain pixels, which are shown here in pink, and allow us to have a much better curve, which is what one would expect as far as the velocity profile through a stenotic aortic valve. And then I can go ahead and click on a velocity which would represent the peak systolic velocity, and it will show me here in the image which pixel corresponds to the highest velocity. And you can see the peak velocity is about 3.7 meters per second, and using the Bernoulli approximations, that corresponds to a peak pressure gradient of about 57 millimeters of mercury and a mean pressure gradient of 34 millimeters of mercury. Now, if I want to march down to see what the second highest velocity pixel is, I can click on this value here, and it will take me to another pixel. The next highest velocity is 3.6 meters per second. The next one is there, and the next one is there, and so forth and so on. So you can interrogate these pixels and make sure you're choosing a pixel that has good signal in it, and so therefore is giving you a reliable value. Now, sometimes there's a problem with aliasing. If the peak velocity exceeds the maximum velocity that was set by the technologist for the scanner, you can get aliasing just like you can in ultrasound or echocardiography. I can simulate that here by moving the slider, and you can see now some of the peak velocities are truncated and aliased. And so if this is the case with the natural acquisition, it's very easy for you in post-processing just to move the window so that you no longer have aliasing. I hope this video was helpful, and if you'd like further details in flow analysis, you can find them under the Help menu in the Instructions for Use as shown here. Thank you very much.